Okay, so the final thing here is Bohr derives this atom. The atom predicts these spectral lines, right? But the remaining question is, why are there only certain orbits allowed? And how is it that electrons can orbit an atom? He called these things stationary states. So how can something be moving and stationary at the same time? And the answer is, and we learned this last year, was that if there are standing waves, the electron is both moving and stationary at the same time. Does that make sense? And I'll show you this again in class, right? But remember those wonderful standing waves I made with a spring last year in front of the class. There were certain modes that were allowed, and there were certain modes that weren't allowed, right? It was this, and then if I sped it up, it went boom. It made a quantum leap from this state to this state. And then if I put even more, mojo into it, right, it would go to this state here, okay? So this was the notion. So the kind of interesting thing is that if you go and read in the book, Bohr just basically just pulls this out and it just says, okay, I'm going to quantize something called angular momentum, which is L. And we don't study this, right? For an object going in a circle around something, the angular momentum is just m times v times r. And this is, beyond the scope of the class, right? And then what he said was that is equal to some integer times Planck's constant over 2 pi, which is just h bar, right? Okay. And so really what you need to understand is that electrons are in a standing wave around the atom. But the cool thing is that this is de Broglie's equation, right? Okay. And if I just set this thing up right, I can actually show that the circumference, right, the 2 pi r, the circumference of a particular orbit is equal to n times the de Broglie wavelength. Well, the de Broglie wavelength is lambda is h over p, right, which is h over mv, right? So the radius or the circumference of the orbit is equal to n times h over mv. Aren't these two equations the same? Aren't those the same? Let me convince you of this, okay? Let's move the mv up there and the 2 pi down there, right? mvr is nh, right, over 2 pi. It's the same thing, right? So the important point is that it's something Bohr used to derive his equation comes from the notion that the electrons are acting like waves, and particularly they're acting like standing waves, like this, right? Okay, and here's a picture, right? They're trying to draw this as a standing wave, and instead of it going like this, they're drawing it as a circular standing wave, right? Which is all well and good, but the electron's not really following a pattern like that. It's actually a probability wave that is, yeah, all right. So that's weird, right? Okay, now IB does this crazy thing, and I've never seen it anywhere else. It's called the electron in a box formula. So you start off with these things, right? The wavelength of these this is L, right? Is this distance here, right? And they say it's 2L over N. Well, N is 1, 2, and 3, right? Here, if you look, this works, right? Because the wavelength is equal to 2L divided by N is 2, right? Yeah, sure enough, this is one wavelength right there, okay? So that works for this, okay? And then the next thing is we're going to use the de Broglie's equation like that, right? And then you can write kinetic energy as momentum squared over 2m. And the reason that works is, why does it work? Because momentum is mv. So momentum squared is m squared v squared, right? And then if you divide by 2m, don't you have 1/2 mv squared, right? Okay. And so now we can actually derive this electron in the box model from that, right? Okay, and it's not hard. Ek is momentum squared over 2m. So momentum is this, right? So I'm going to go Planck's constant squared divided by the wavelength squared, right? Divided by 2m. So I just substituted this in for the momentum, right? Okay, and then the wavelength, now we just have to substitute this in for the wavelength, right? So that equals h squared divided by, well, 4 L squared divided by N squared, right, divided by 2m. And then, of course, to resolve this thing, right, we're going to flip this around. Then the n squared is going to go in the top, right? So ek is equal to h squared n squared, right? And then 4 times 2, this is going to go down in the denominator, right? So you're going to get 8 m L squared, like that, where L is the length of the box, right? This is L. N is some number, like 0, 1, 2, 3, etc., right? Okay, this is Planck's constant. That's the mass of an electron. Okay, so, I don't know how important this is to IB, but there it is, and they've got it in the data packet. So if electrons are in a box and oscillating as a standing wave, this would be their energy. This is sort of related to the Bohr atom, right? Okay, so let's try this example, right? What's the kinetic energy of electron in the ground state, right? Well, for the ground state, n is 1, right? In a box, it is 0.1 nanometers in length. So that's an atom, right? That's 10 to the, L is 10 to the, 1 times 10 to the minus 10th meters, right? That's 0.1 nanometers, because nano is 10 to the minus 9th. Right, so now we just have to plug in, right? Equals 1 squared times 6.626 e minus 34 squared divided by 8 times the mass of an electron, 9.11 e minus 31 kilograms, right? Times L squared, so that's 1 e minus 10 squared, right? What is that? Well, 1, don't forget to square your 1, times 6.626 e minus 34 squared divided by parentheses 8 times 9.11 e minus 31. Okay, times 1 e minus 10. That thing squared, right? Right parenthesis. And I get 6.02 times 10 to the minus 18th joules, which is remarkably similar to what I got there, right? Okay, so there it is. For what it's worth, if an electron acted like a standing wave, as in like fundamental, right? Et cetera, right? If it acted like that, this would be its kinetic energy. Not sure why they have that right there. So let's just go into Schrödinger, right? Schrödinger eventually comes up with a wave equation for the hydrogen atom, right? And solves that, right? So the electron is represented by a wave. And here's the deal, is that we can actually solve it. We can set up the equation for any atom we want to, but we can only solve it for hydrogen and singly ionized helium. Remember, singly ionized helium has, 2 protons, 2 neutrons, right? And then it has 2 electrons, but if it's singly ionized, it has 1 electron, right? So it's just like a hydrogen atom with 2 charges in the middle, right? We can solve it for that, but anything that's got more than 1 electron, we run into the nasty little problem that an electron here is going to interact with an electron here, right? So the electron-electron interaction makes it essentially unsolvable, which doesn't slow us down too much. We've got computers that can get the answer to us. We just can't get the equation, right? Now, these things are really bizarre. When we talk about these solutions, they are, it's like a high probability of being here, less of a probability of being there. So it's a bit like the blades of a fan, a fast fan, right? The electron's not everywhere. It's just there's a probability of it being a certain place. So if you put your finger in the space where the fan is spinning, eventually your finger will get hit, right? Okay. When you solve these things, here's some solutions of the Schrödinger wave equation. They're just bizarre little shapes like this, right? So here are the quantum numbers, right? And you might have studied those. And this is the spatial probability of those things. So they're just these bizarre things. But, they are there, and they have been supported by scientific evidence. So there you have it.